Good day, class. Today I'm going to show you how to draw a shear force diagram and bending moment diagram, for a beam. So we have a simply supported beam, point A and point B, with the span of 7 meter, and on this beam it has 3 load. The first load will be P1, point load 1, which is 40 kilonewton, and we have point load 2, 10 kilonewton, and we have an uniform load U1, with the value of 5 kilonewton per meter. The position of the load is as displayed in the diagram. So by following the equilibrium formula, we know that sigma MA equals to 0. So we'll go into calculating all the moment that will act on point A. The first moment will be coming from point 1, P1, which is 40 kilonewton times 3 meter. So this is because you have to calculate from the load, times the distance from point A, because we are using point A as our point of reference. The next thing will be P2, 10 kilonewton times the distance from point A, which is 5 meter. Plus, this time we have to convert the uniform load U1, into a point load acting at the middle of the span of that particular uniform load. So how do we go about this is that 5 kilonewton per meter times 3 meter. This is to get the total load coming from the uniform load 1, U1. Then we have times the distance, the new distance, which is 3 meter divided by 2. As you can see, the newly converted uniform load will be acting at the middle of the span. That's why you have to times 3 meter divided by 2. And the last one will be the reaction force, RB. So we know that to counter all the load, we'll have RA and RB. So RB will be a anti-clockwise force. Therefore it is a negative force. Again, we have to times with 7 meter, which is the distance from point A. Again, following the formula, the whole equation, will equal to 0. So we rearrange the equation, in a way that, 7RB equals to, 40 times 3, which is 120 kilonewton meter, plus 10 times 5 meter, which is 50 kilonewton meter, plus, if you sum up all this, it will equals to 22.5 kilonewton meter. Remember that, you should always write down your dimension, so that you will not confuse. Later, you will try to get RB by factoring with the number 7. Therefore, you get RB as 27.5 kilonewton. Okay, so now we have our RB. Okay, since we know that, okay, based on the equilibrium theory, okay, we know that whatever load that is acting on the beam will be counter-reacted by the reaction force from support A and B. Therefore, the total load, okay, the total imposed load on this particular beam, okay, is equals to the reaction force A plus reaction force B. Okay, therefore we know that total load equals to RA plus RB. Okay, from this formula, okay, we can find RA, okay, by using the total load, okay, to deduct RB. Okay, therefore we have RA equals to first load 40 kilonewton, 40 kilonewton plus 10 kilonewton, okay, plus 5 kilonewton per meter times 3 meter. Okay, and then we have to minus RB, which is 27.5 kilonewton. Okay, so if you solve this calculation, okay, what we'll get is 37.5 kilonewton. Okay, so this is our RA. Okay, so once we have RA and RB, we can start to work on our shear force diagram. Okay, by using a graphical method, okay, we can draw the shear force diagram, okay, on support A, okay, with value of 37.5 kilonewton. Okay, so try to draw. Okay, and then we'll put the value 37.5 kilonewton, okay, at here. Okay, so what happened here is that we have a uniform load of 5 kilonewton per meter. Okay, what this uniform load will do, okay, to the shear force is that, okay, it will create, okay, a force of 5 times 3 meter. Okay, so we have a force of 15 kilonewton. Okay, therefore the value 37.5 kilonewton will be deduct with the number 15 kilonewton. Okay, and the value we'll get will be, okay, 22.5 kilonewton. Okay, so what happened here is that, okay, now we have a point load 1, okay, P1 equals to 40 kilonewton. What P1 do to the shear force diagram is that, okay, we'll have to use 22.5 kilonewton to deduct 40 kilonewton. And the value that we'll have will be, okay, negative 17.5 kilonewton. Okay, and when we look at this band, okay, there's no force, okay, on this 2 meter span. Okay, therefore the shear force will stay the same. Okay, so how we go about this is that we draw one straight line, okay, until we reach the third point. Okay, at this point, okay, we have point 2, a 10 kilonewton acting here. Okay, therefore we'll have to deduct 10 kilonewton, okay, out of negative 17.5 kilonewton. Okay, so what we'll get here is negative 27.5 kilonewton. And again, there's no more loads acting on the last band. Okay, therefore the shear force diagram stays the same, and it is still 27.5 kilonewton. Okay, at this point, we can double check whether our shear force diagram is correct or not by checking the last value with our RB. Okay, if you find that the last value, negative 27.5, okay, is the same as 27.5, that means the whole shear force diagram will go back to 0. Okay, if you can complete this, that means your shear force diagram is correct. The next step, okay, is to do the bending moment diagram. Okay, as we know that, okay, the value of the bending moment basically is the same as the area, okay, in our shear force diagram. Okay, so let us try to calculate the area for this zone, okay, which is 37.5 plus 22.5 divide by 2, then times the span 3. Okay, the answer will be 90 kilonewton meter. Okay, 90 kilonewton meter. And by looking at this diagram, if the line here is a linear line, okay, in the bending moment diagram, we'll draw a curved line. Let us go to the next section in our shear force diagram. Okay, we calculate this area, okay, which is 17.5 kilonewton times 2 meter. Okay, so what we'll have here is that the total area deduct the new area will get a value of 55 kilonewton meter. Okay, and you see that since it is a straight line in the shear force diagram, okay, therefore we'll draw a linear line in our bending moment diagram. Okay, so that we draw a linear line. Okay, so to complete the bending moment diagram, okay, we should calculate the last section, okay, which is 27.5 kilonewton times 2 meter. The answer will be 55 kilonewton meter. Okay, following the equilibrium theory, okay, we'll draw a linear line goes back to point 0. If you can draw this, that means your bending moment diagram is completed. Okay, thank you for your attention.